Welcome to Today we're going to talk about power trips. Let's give the big view first. How powers fit into the number landscape. Imagine a place called Numberland. All the numbers love to come to Numberland. Oh, we have all kinds of numbers that just want to come and play around in Numberland. And the letters too. First they like to come to Timesville. When they go to Timesville, they find that there are quite a few things for them to do. Timesville are where terms gather. Factors like to be in Timesville. And in fact, let's take a look at some of the rides that numbers like to do when they come into Timesville. They can go play on the power tilt-a-box. They can play on the division roller balance, the multiply roller coaster. They can play on the square root dive. Notice, square roots, division, powers, multiplication are all related to times. Factors, terms, all love to play in here. And remember, in Timesville, 1 is no 1. That is 1 when it does times, when it does all these things. Powers, square roots, square root of 1 is 1, 1 squared is 1, 1 divided by 1, 1. 1 doesn't seem to have any effect in this land. 1 is a no 1. Now, let's go over to another land that the numbers love to come to. They love to come over here to Plusville. And even letters like to play here. They only have a very limited number of activities they can do here. They can add on our plus pounder. They can subtract on our minus masher. They can add and subtract to their heart's content. But that's all. And notice, of course, that 0 is no hero here. 0 adds to things, doesn't matter. 0 subtracts from things, doesn't matter. 0 is nothing in this land. Also, in this land, we call things add-ins. Remember, over in Timesland, we called things factors. This bridge between the two. Notice all the strange expressions we can get when we combine things from Timesville and things from Plusville. We have a plus b squared. We've got adding, we've got powers, we've got adding and powers mixed in another way. We've got division, 1 over b, combined with addition. We've got adding, squaring, square rooting. These kind of complicated expressions have to be handled very carefully because they bridge between the two lands. And we'll mention a little more about that later. Now remember, the main topic today is powers. That is, we're over here in Timesville. We're going to look at these powers in great detail. Let's go. Let's talk about powers. You've learned that a to the fourth equals a times a times a times a. And this is a fairly well-known idea. Look at it in a little more detail. This a is sometimes called a base. Notice each of these a's are factors. We are in Timesville, so we want to use that terminology. This 4, if you think of it, is a factor counter. And, you know, you can think of these a's as kind of like, first of all, stuck together pretty tightly, and I like to think of them as a string of beads. Let's look at a string of just any beads that we might put together to make a necklace or bracelet. Like this. I speak of these as a string of A's, and sure enough, they're just as if you had strung some A's together to form some kind of bracelet or necklace. We're going to refer to these as strings, and let's now look at some characteristics that the powers have when they're working on various letters. When we have a to the fourth times a to the third, for instance, well, we have our string of 4 A's. I'm joining to it a string of 3 A's. I'll put a little dot here that means we're joining to it. It doesn't matter if that dot's there. A string of 3 A's. Well, of course, that only means that we have a necklace or set of beads that makes 7 A's in a row. And we notice that these factor counters just add up, and we write a to the 7th. That's a pretty straightforward way of counting factors. This whole string of factors is called a term. Remember, we're in Timesville. Strings of things are called terms. And I'll borrow a few A's here, put a few B's on together in the string, maybe even a few C's. This is a string of beads, but all these beads are different from each other, and so we have to write it this way: 4a squared, b squared, c squared. Every time we change to a new kind of bead, We have changed what's called the base, and we still have a string though. This is all called a term. Another idea here is what happens when we have a to the 6th over a to the 3rd. The dividing. All those are in Timesville operations, so we don't expect this to be too complicated. Let's make a string of a's on top, a string of a's on the bottom. You've learned in all your study of fractions that if we remove a same factor from numerator and denominator of a fraction, the fraction stays the same value. Well, we can do that again. We can do that again. Now notice when all the a's are gone on the bottom, we don't write 0, because after all, we are in times land. So we write 1. 1 is a no one that is accompanying all these factors on the bottom, and when all those factors disappear, there's still the 1 holding that place. And all that's left now is an a to the 3rd power, counted up by the factor counter on top, and a 1 on the bottom. And this is, since 1 has no effect in times land, we have a to the 3rd. So this is another rule that you just learned, that whenever we divide, we can simply subtract those powers, those factor counters. Another situation that you have learned about is a to the 4th to the 3rd power. What does that mean? This is a power to a power. It means that we have a factor counter that is saying a to the 4th are factors being counted. So we have a to the 4th times a to the 4th times a to the 4th, all being counted 3 times by that counter. But then these a's, of course, are being counted by their own counters. And really, we have a necklace stringing thing going on here. We notice here that, in effect, we've strung 12 a's together. And certainly we notice that we could have done this much faster by simply multiplying the 4 times the 3. So far we've seen ways in which we add powers, we subtract powers, we multiply powers, depending on which kind of situation we encounter. There are some special situations I want to talk to you about. What about this one? A to the 0. What should that equal? Well, there's 0. There's the nobody from Plusville. However, we are still in Timesville. This is saying there are no factors a being counted. Well, if there are no factors a being counted, of course, we just saw earlier that means there's still a 1, because 1 is the no one of multiplication land. So a to the 0, and indeed any factor being counted 0 times, means there's still that 1 that's really a no one. Here's another one, of course. A to the 1 means there's just one bead being strung. That's easy. Now this is a complicated looking situation here. We have a to the 3rd plus a to the 4th. Actually, it looks almost like you want to say a to the 7th. Let's see what that looks like with beads. We have 3 a's here, and we have 4 a's here. But you know, we're not being told to string those together on a necklace exactly, because we have this funny thing interrupting the stringing here. We have that funny thing from a different realm interrupting the stringing. We can't really string those together and say we have a to the 7th. We've got an interruption in our string of beads. So there's a warning here. We can't simply add that 3 and 4. What can we do then? And actually, this is called a term. This is called a term, as are all clumps of factors from Timesland. But we have a plus between them. This is called adding two unlike terms. They're called unlike when they have different letters in them. So we can't combine these in any simple way. Now I know you might be a little concerned about this, so let me talk about this for a minute. Let's look at what happens when a is 10. Let's see what happens here. Well, 10 to the 3rd is 10 times 10 times 10. 10 to the 4th is 10 times 10 times 10 times 10. Let's add those together. Now, is that 10 to any power? I hope you can see that that's not 10 to any power. You see what happens? Sure, we can add them together. We just don't get 10 to a power. So these are called unlike terms. They don't create anything that resembles them when you add them together. Therefore, we leave a to the 3rd plus a to the 4th alone. Let's look at another couple of situations. We have a squared, b to the 4th, all to the 3rd power. What does that mean? Well, this 3 is the uber counter. It's the factor counter that's turning all of this into factors being counted 3 times. Let's see what that looks like. Let's count them 3 times. Now you know from your study of multiplication that you can multiply in any order, so we could multiply them all like this. String those beads in this order. After all, these are nothing but a string of A and B beads, many A's and B's strung on a necklace. I'm restringing them on the necklace this way. And then this, of course, means there are 6 A's strung together, and there are 12 B's strung together. And we can see that we could have accomplished this a lot faster than writing all of this by simply multiplying 2 times 3 and 4 times 3. That's just a little variation on our power rule, that when we have an uber power, we can multiply each power in the parentheses times the power outside. This is a common tripping point for many. Negative 4 squared and negative 4 squared do not give the same answer. We know this says there are 2 factors called negative 4. Negative times negative is positive, so we get 16. But here, because of the order of operations, we say that this 2 happens to the 4 first. 4 squared is 16, and then we get a negative. Be careful about that. Let me give you a quick memory device. You remember your order of operations. Here they are, parentheses, powers, times and divide, but in either order depending on how they appear in the sentence, and plus and minus in either order depending on how they appear in your sentence or in your expression. And what we've learned about powers is that if we're trying to take the action of multiplication of 2 objects that have powers on them, we experience a downshift. We get times downshifting to plus. That's what the powers do. We get division downshifting to minus. That's what the powers do. We get powers downshifting to multiplication. And if you try to downshift and do an action of adding like we did those unlike terms, we see there is no downshift. So we can't do it, and therefore we leave them as unlike terms. So enjoy building your power with powers. Some things you might want to tackle in the future are negative powers. You might want to do some mixed realm expressions. Those are the ones that we saw on the bridge between Plusville and Timesville. You might want to tackle some fractional powers. And there, of course, are our old friends, the roots. Until then, keep building your power with powers. See you later.